Okay, got 4 problems solved. I want to look at them, and if you're doing this as a distance student, go ahead and solve this. I'm going to move right into the solution, so if you're doing this by video, do the solution. And then you pause, then you can see what happens. Okay, so here we go. X squared minus 6x minus 7 equals 0. Okay, well, this is the form ax squared plus bx plus c equals 0. For a is the number in front of x, or the coefficient of x squared. There's no number in front of x squared, so we say the coefficient is 1. B is the coefficient of x, which is -6, and c is the number, the constant number, doesn't have a value of x on it. C is -7. So that quadratic formula tells us x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So that x equals negative of b, which is itself -6, the negative of -6, plus or minus the square root of the square of -6. Make sure we see that negative in there. Minus 4 times a times c. All that divided by 2 times a being 1. And then we just do the arithmetic. If we get 6 plus or minus the square root of 36 plus 24 over 2. And that equals then 6 plus or minus the square root of 60. Oh, wait a minute. I messed up. I've been looking at this and I know that thing factors, and I know how it factors. So it couldn't have been right. I couldn't find my error. But that should be -7 there. And it's 28. And now we have the square root of 64. It's going to work out. Okay. Be careful. Be methodical. Don't just write down whatever number pops into your head like I did. In any case, this is 6 plus or minus square root of 64 is 8. All that divided by 2. Make that 2 by 2. Okay, so x is 6 plus or minus 8 over 2. So x equals 6 plus 8 over 2, which equals 14 over 2, which is 7. Or x equals 6 minus 8 over 2, which is -2 over 2, which is -1. Now we check. That's always part of doing the problem, and I think people strongly tend to skip that step. If you don't check it, then you don't catch your errors. If you do check it and find that it doesn't check out, then you find your error. Maybe there's an error in what you did when you checked. Maybe there's an error in what you did when you solved the equation. Okay, so we check. If x equals 7, then we get 7 squared minus 6 times 7 minus 7 equals 0. Put a little question mark on that because we're testing. Is this equal to 0? If we don't get 0, that means our solution's wrong. Okay, well, this gives us 49 minus 42 minus 7 equals 0. and 0 equals 0. When you get done doing the arithmetic, negative 42 and negative 7 is negative 49, so we have 49 minus 49. Now, you should probably write that stuff out unless you're very good at doing the arithmetic in your head. And then if x equals negative 1, we get negative 1 squared minus 6 times negative 1 minus 7 equals 0, which is 1 plus 6 minus 7 equals 0. And I think anybody can see that 1 and 6 make 7. So 7 minus 7 is 0, so it fits. And now we're done. We're not done with the problem unless we've done the checks. And again, one of the big problems with a pre-calculus class is typically people don't check their work. They just believe whatever they got, and they never get the feedback they get from checking and debugging their work. So don't learn it as fast, even though it takes extra time to check. Okay. So that's the first problem. Now, the second problem, or something, and actually do it here. And I did write at least the expression for the quadratic formula here, which is there for reference. And I gotta know this, but it's only been 2 days since we introduced it. So I'm going to give it to you, but on a test or on future quizzes, you just got to know it. Okay. And you know it if you do a lot of problems because you keep writing it down. And when you do the problems, you don't sit there with the quadratic formula in front of you so you can write it down without engaging your brain at all. You put it away and you try to write it down. Then you look back and check. Okay. And if you got it wrong, well, you've got feedback. So you keep doing that until you start writing it out correctly every time, and so that your problems check out every time. Okay, so we have then x over 3 minus 4 over x equals 6. Immediately, you find your common denominator, which is 3x. And you multiply both sides by a common denominator. And well, 3x times x over 3. Now I'm going to put some dots down here because I don't want to keep repeating the same thing. But well, actually, let me write out the distributive law and we'll do the dots. Okay, 3x times x over 3 minus 3x times 4 over x equals 3x times 6. Because the 3x multiplies this and it multiplies this. Okay. Now, you're going to end up with a 3x squared in the numerator and a 3 in the denominator. So I could actually write this 3x squared over 3 minus 3x times 4. Well, you multiply 3x times 4, you get 12x over x equals 3x times 6. 3 times 6 is 18. You get 18x. Then you divide the numerator by what? 3 is a factor of the numerator. It's one of the things you multiply to get the numerator. 3 is a factor of the denominator. It is the denominator. So you can divide the 3 into the 3, leaving you just x squared. X is the denominator. X is a factor of the numerator. It's something that's multiplied by everything else in the numerator. And you get 12, and this is supposed to, yeah, this is x squared, but there was a 2 up there where I couldn't see it. Okay, so you get x squared minus 12 equals 18x. Now at this point, it doesn't look like this. It's not in the ax squared plus bx plus c equals 0 form. But we can put it into that form just by getting 0 on the right-hand side. So we do x squared minus 12 minus 18x equals 18x minus 18x. so that this side ends up 0. And this side, we could leave it like this. And but usually we write it in descending powers of x. And we're going to write it as x squared minus 18x minus 12 equals 0, because then it's just easier to match up your A, B, and C, and you're less likely to make an error. So now this is standard. Quadratic form. Ax squared plus bx plus c equals 0. And actually, I should probably call it general, but it's the usual form. And we can identify A, B, and C. A is 1, B is negative 18, C is negative 12. And we just do as we did before. I'm not going to go through the details. And we get the result. Okay. So that's what we do when we have an equation like this. Well, whenever we have an equation with denominators, we multiply by the common denominator. Having multiplied by the common denominator, we get an equation down here with no denominators, and we see that x squared, and we see an x term, and we see a constant term. They're scattered over two different sides of the equation typically, but then we just do what's necessary to get 0 on one side, and we can rearrange it into the form of a quadratic, the ax squared plus bx plus c form. So we need to know this. Okay. Now, I could dispose of this one very quickly. And I'll dispose of it just right now, but then I'm going to do something with it. Okay. It should be obvious that if x equals 5, you're going to get 0 here. And 0 times whatever you get here is going to give you 0. Because when you multiply by 0, you get 0. And if x plus 3 is 0, you're going to get 0. And x plus 3 is 0 if x is negative 3. So it's very clear that the solutions are 5 and negative 3. So x could be 5 or it could be negative 3. Well, let's write this one out a little bit more. Okay, so we have the way I will write this solution is this way. And of course, this is the way we did it last time. I wrote a minus here, it's a plus. Okay, so it means that if two things multiplied are 0, then one of them has to be 0. Could be either one, so it could be this one or this one. Well, it's very clear that we can solve these very easily. Add 5 to both sides here, we get x equals 5. Subtract 3 from both sides here, we get x equals negative 3. Okay, that's our solution. Now, if we wanted to do this the hard way, and we don't want to do it the hard way, so you might ask why I'm doing it the hard way. I just want to connect this with the quadratic formula and understand that you get the same thing and kind of lead us into the whole idea of factoring. Okay, so we start with this equation. We apply the distributive law. We get x times x minus 3 minus 5 times x minus 3 equals 0. And then we use the distributive law again. X times x minus 3 is x squared minus 3x. Negative 5 times x minus 3, well, negative 5 times x is negative 5x. Negative 5 times negative 3 is plus 15. And that equals 0. So we get x squared minus 8x plus 15 equals 0. And now we can use a quadratic formula. I'll just kind of abbreviate things. A is 1, B is negative 8, C is 15. X equals then the square of negative 8 plus or minus the square root of the square of negative 8, the negative of negative 8 plus or minus the square of negative 8 minus 4 times 1 times 15, all divided by 2 times 1. Well, when you work this out, you're going to get 5. So I'll say equal with a couple dots, and you finally get 5 or negative. So you can work that out. See that it's so. Now, we haven't talked about factoring as we probably should, but factoring is one of the few things that seems to be emphasized in such a way on the SOL or whatever it is that drives so-called education. People are usually pretty good with factoring. And the point is that if we take this expression and factor it, this is what we get. So if you can factor a quadratic equation into like this form, you can save the arithmetic here. You can write it out like this and you can quickly get your solution. But that's of limited value in the real world because most quadratic equations don't factor. And you end up having to use the quadratic formula. Okay. So. Okay. Now let's take the last problem, 2x minus 4 times 6x minus 2 equals 0. What are we going to do with this? With this, we do the same thing we did here. If two things multiplied give you 0, then one of them has to be 0. Well, we say one got to be 0. So this splits into two equations. 2x minus 4 equals 0. Or 6x minus 2 equals 0. We can solve that easily. We get x equals 1/2, or x equals 1/3. Okay. And there it is. Now, if we expanded this and applied the quadratic formula, and I recommend that when you do these, you do both the solution and the alternative solution. You'll learn a lot by doing that. Now I'm skipping some steps here. This gives us 12x squared minus 28x plus 8 equals 0. So that x equals negative of negative 28. plus or minus the square root of 12 squared minus 4 times 12 times 8. Something seems to be wrong here. And it's not 12 squared. It's negative 28 squared. You see there, this not being very careful. Okay, well, it might be a little hard to read, but you understand what needs to go there. Oh, 2 times 12. Well, it's hard to see how we're going to get a half and a third out of that. What am I doing wrong? Well, so be it. You work this out, and if I've written it out correctly, first of all, 28 squared is what? 784. And this is 48 times 8, which is 484. And 84 minus 484. 300. That doesn't all work out right. And I don't have room. But the result should match 1/2 and negative 1/3. Let me look at my numbers again to see. I think this must be 884. So that you get the square root of 400 here, which would be 20. And I think that would lead you. Okay. This shouldn't have been x equals 1/2. This should have been x equals 2. That works out. Okay, there it is. Anyhow, the idea is you can solve it this way by splitting it into 2 equations, because either this has got to be 0 or this has got to be 0, and that's what this says. Or you can expand it and use the quadratic formula, which is a lot more work. But that's one way to check it. If the quadratic formula gives you the same thing that this gave you, chances are that you did it right. Okay, there are very few steps in this that mimic steps here. So if you do something wrong in one, you're unlikely to have done the same thing wrong in the other. Okay. Now that's what we need to know about solving quadratic equations. If you know that much, then you're going to be pretty much okay in pre-calculus. Now, there is some factoring involved, and we might address factoring a little bit later. But right now, we've got to assume that you know how to factor, or will refresh your memory on how to factor when you get into pre-calculus. Okay. Now we need to move on to talk about quadratic functions. Okay, quadratic functions. First, I'm going to define the quadratic function. Notice. Use the wrong word here. Didn't realize it until I started to write the same word here. Vertically stretched. Well, let me read it to you. I should have probably written that out when didn't have the camera, but quadratic function, one represented by vertically stretched, vertically shifted, horizontally shifted basic toolkit function, scoring function. Okay, there it is. This gives us the function g of x equals a f of x minus h plus k equals a times x minus h squared plus k. Now, this is something, if you're in my class especially, that should click immediately, because we spent a lot of time developing the whole process of shifting and stretching functions, not so much stretching as shifting, but we're talking about stretching as well. But in either class, you would have the f of x and if you want to a little bit out of order here, but remind you that f of x is x squared, so that f of x minus h is x minus h squared. So there it is. The graph of this function. Well, we construct the graph by taking the graph of the squaring function, which in my class we sketched within a square. And in other classes, I sketch by plugging in numbers into the formula either way. In my class, you'd be required to do the construction. In other classes, you probably wouldn't talk about the construction, okay? So you talk about f of x equals x squared and make a table. X equals -2, -1, -1/2, whatever. So there it is. Here's y equals x squared. Then you vertically stretch this graph. Okay, and maybe you reflect across the x-axis, and maybe you do some other things. That's all taken care of by this number a. This number a dictates that the graph gets vertically stretched. That this rectangle or this square, whatever it is, gets longer or maybe gets shorter. If a is bigger than 1, then it's going to get bigger. If a is less than 1, then it's going to get smaller. And if a is negative, it's going to flip over onto the other side of the x-axis. Well, we'll address some of that, but this is the basic scheme. So we take this graph, and then we take, I just like to think of taking the vertex, and we move it h units horizontally, and K units vertically. Here H would be positive, K would be negative. And then we can resketch our rectangle here. It's about that high. So it's going to be as wide as the original one. It's going to be about this high. And the graph is going to look like this. So here the graph is, and I probably should use a different color here. So I'm going to make this curve a little bit purplish. So this graph is can we see that? Probably, maybe, not quite. Come on, move over a little bit. We go. Okay, that's better. Vertically stretched. Your basic toolkit is y equals x squared. We vertically stretch it. Then we after vertically stretching it, we horizontally shift it. Now, there's something we learned to do in chapter 1. Okay, something we spent a lot of time trying to get people to learn to do in pre-calculus, and people didn't do the work, and it didn't. Most people didn't do the work, didn't practice enough, so didn't really have the effects that I hoped. But that's simply the case. Okay, so anyhow, there we have it. All right. That's the picture of a quadratic function. And you can put this shape any place you want in the XY plane. And you can also shift it upside down. So I'll just say for negative A, okay, if A was negative, you have this. The vertex would still be here, but everything flips over the x-axis, which gives you points here, here, and here. And you get an upside down parabola. Then we horizontally shift it. And maybe we vertically shifted, maybe by about the same. So we shifted H units, we shifted K units. Here's the vertex. In my class, we have a standard red dot at the vertex, but it works whether you are in my class or not. You put a red dot at the vertex just to distinguish it, because the vertex is very important point. Okay, so here then we have same rectangle, didn't do a real good job of it. And let's go ahead and sketch our curve. Okay, so there it is. If A is less than 0, it's like this. If A is less than 1, then you shrink this box down and it'd be, look wider. Okay, all that stuff. Stuff again, that you should be familiar with, from chapter 1. Okay. Now, so what? Okay, what's the big deal about this? Well, let me try to give you an idea. Let me find some clear board here. First of all, g of x is a times x minus h squared plus k. If you square x minus h, you get x squared minus 2xh plus h squared plus k, which is then a x squared minus 2ax h plus a h squared plus k, which equals ax squared plus bx plus c, where b is all this stuff except the x. C is AH squared plus K. And I just write this down to show you that if you square one of these, when you have the actual numbers for A, B, and C, you're going to end up with an AX squared plus BX plus C. Now, there's a proof involved in this, but I'm not going to burden you with that at this point. So the end result of all this is that a function g of x equals ax squared plus bx plus c has its vertex at the vertical line x equals h, but what's h? H is negative b over 2a. Now b is 2ah, then b over 2a is h. And negative b over 2a is negative h. And what I just said isn't right because I didn't have my negative here. B would be negative 2ah, but you know, b is negative 2ah, this works. So you can believe it, but you don't really have to understand that. That's kind of a proof that this works. So you can accept, if you believe that I can do this, what in my perspective is a very simple proof, but not so simple if you're a pre-calculus student at this point. If you accept this, then you can run this by any mathematician in the world and they'll confirm it, okay? Then you can immediately say something really important about a function. So let's just take an example. Let's see what we can do with this. Let's suppose G of x is x squared plus 6x minus 12. Okay. Okay, let me back up 1 second. This vertical line is called the axis of symmetry. So now, I'm going to stop a minute. Just take this. Vertical line x equals h equals negative b over 2a is your axis of symmetry. Okay. So for this function, what's negative b over 2a? I'll even write this out now. Axis of symmetry is x equals negative b over 2a. Okay, well, A, B, and C. A is a coefficient of x squared, B is a coefficient of x, C is a number that does have an x in it. Okay, so we don't need C at this point. We have A, B, and C. X equals negative 3. They're going to sketch me a graph. Just slop down a set of axes and make a vertical dotted line. X equals negative 3. Now there's sketch the line x equals negative 3. That's your axis of symmetry. Start out in x and y axis. You don't have to put numbers on it. You just put this down and then the numbers will follow. Okay, so x equals negative 3. You don't have any scale on this axis yet. Okay, we're just going to pick a place to put x equals negative 3, and the only real requirement is that it be to the left of the y-axis, because that's where the negative numbers on the x-axis go. X is 0 here, positive here, negative here. Well, I don't want to put it too close to the y-axis. I don't want to put it too far from the y-axis. So I'm just going to kind of put it halfway along whatever I drew for the x-axis. And then we'll see how it works out. So now we've got a scale for the x-axis. If we divide the interval from here to here into 3 equal parts, we can do that. Okay. So, that's how big 1 is. So I can put x equals 3 out here, same distance to the right as x equals negative 3 is to the left. I could put a couple of them. Okay. So there, I've already got a scale on my x-axis. I don't have to do that, but I did. Okay. All right, so now I know this is the axis of symmetry. The vertex is on this line. All right. So how do you figure out the y coordinate of the vertex? And to find the y-coordinate of the vertex, you say kind of, well, okay, well, x equals -3, then this is a function, of course, y equals g of x, y equals g of -3. Every time I try to make that g look better, I make it look worse. But tell me then, what's g of -3? I had something that you could identify as a g, but it looks like a q now. Not positioned very well, but it's g of -3. So evaluate g of -3 for me. Okay, now some people seem to have lost track of what function we're dealing with. We're dealing with this function, okay? And we use the -b/2a to find the x equals -3, which is the axis of symmetry, meaning that our graph is going to be divided in half. It's going to be a parabola, symmetric on both sides of this line. But we want to find out where the vertex is. Okay, and the vertex is on this line because that's where the vertex of a parabola is. Okay, and I could do a lot of because here, but don't want to get too complicated on it. Okay, so we want to do g of -3. Now people have trouble with this, probably because I haven't written down g of x up here. Of course, I'm going kind of fast, you might not have had time. So let's just make sure we understand. Okay, we've got g of x equals x squared plus 6x minus 12. The axis of symmetry is x equals -3. G of -3 equals what? There's g of x. And we do g of -3. Okay, what's g of -3? Well, we plug in -3. Here we get -3 squared plus 6 times -3 minus 12. And then we evaluate it. We get 9 minus 18 minus 12, which is, I think, -21. Is that what you got? -21. Okay, good. Okay, so now we know that we could let y equal -21 here. Now our x scale and our y scale are very different. Maybe too different. Draw this thing reasonably. But I'm not going to let that stop me. Okay, so you got y equals -21. Now, tell us that our vertex is here. At this point, if you're in my class, and if you're not, you can just kind of ignore this. You can figure out that, okay, y equals -17 maybe here. X equals 1. X equals not 1, but -1. And now we've got lines that bound a 4x4. Square that doesn't look like a square because my y scale is different than my x scale. And I can sketch facsimile of the graph. Here. Now, this graph is going to continue. If I've sketched this right, and I doubt that I have, and not too far wrong, I'm going to guess that it comes up about like so and intersects the x-axis here, and maybe similarly over here and intersects the x-axis over here. And I can estimate where that is. If this is x equals -3, well, that's x equals a little over 1, between 1 and 2. Over here, let's say that's -5, negative, maybe around x equals -7. So that's reasonable, but we don't know for sure. Well, what do we do to figure out what the shape of this graph is in general down here? But we don't need this rectangle, but if you're in my class, we've used it, and I wanted to mention it. Again, you can ignore that if you're in a different class. One way or another, it looks like our we have two x-intercepts because our vertex is below the y-axis and the parabola opens up. Now, I haven't really addressed the coefficient of x squared. But right now, we'll just go with what we have. And what are the x-intercepts? Well, x-intercepts and y equals 0. Well, y equals g of x equals x squared plus 6x minus 12. So if y equals 0, we get this quadratic equation. And we find that x equals -6 plus or minus the square root of 6 squared minus 4 times 1 times -12 over 2 times 1. And that's -6 plus or minus the square root of. It'd be 36 plus 48. Well, I think that's the square root of 84 over 2. The square root of 84 is like 9.1 or 9.2. I'll say maybe 9.2, but it's kind of tricky. Okay. So if we could calculate this, it gives us 1.6 or -7.6. And that can't be, yeah, that can be right. No. 15.2, 7.6. Okay. Okay. Well, it turns out that, agrees pretty well with what I drew based on this. Now, there's no reason for me to have expected that it would, except I kind of know the way a parabola is shaped after hundreds of years of drawing them. But this tells me that we have the point then 1.60. Now, with the scale I drew, that should have been just a tad bit to the right. And where can I label this? I guess I'll just label it here. -7.60. Also, the y-intercept occurs when x equals 0. And if I put 0 in for x, these are both 0, I just get -12. So this point should be the y-intercept. It's on the line. Y equals -12. Now observe that -12 shouldn't be closer to -17 than 17 is to negative 21. It should be a little further. So the graph isn't totally correct. It isn't totally right, but it's a good schematic. So I can say that this point is 0, negative 12. Okay, well, that's kind of a lot to digest, but it's actually fairly simple. If you need to ignore the reasons for this, you just axis of symmetry is at negative b over 2a. That's one. For any quadratic function, you can find its axis of symmetry, okay? And you can sketch it. And then you can plug the coordinate of the axis of symmetry into the function and find the y coordinate of the vertex. And I never did write that out. X is negative 3, y is negative 21 on this line. So that this point is negative 3, negative 21. Then if you have the skills that hopefully people are developing in my class, you can do this. But whether you can or not, you can then find the x-intercepts, because x-intercepts always occur when y equals 0. So you set this equal to 0, and you get the x coordinates at which the graph intercepts the x-axis. Finally, it's very easy to get the y-intercept. The y-intercept occurs when x is 0. You plug in 0, you get the y coordinate, and the x coordinate, of course, is 0. And if you put that picture all together, that's a pretty good picture of quadratic functions and quadratic graphs. Okay, now there's one other topic we need to touch on briefly. And for the most part, you'll need to get this. A lot of this by reading and doing the open math. But let's take this. Okay, that's a function that I'll call p of x. Whether it's x-intercepts or is the y-intercept. There's only one y-intercept. Okay, so how do you find x-intercepts? Well, just like what we just did, x-intercepts occur when, yeah, I did in the back of this board, didn't I? X-intercepts occur when x is y is 0. So we solve this equation. How do we solve this equation? You've got three things. You multiply them out to give you 0. That means that one of them's got to be 0. Maybe it's this one. So maybe x minus 3 is 0. If not, then, well, maybe it's this one. If not, then it has to be this one. Got to be one of them. Now, when you do this sort of thing, I want you to write it out like I'm writing it out. Put the ors in between here so you think about the logic. Okay. Well, then it's easy to find what the zeros are, because, you know, x minus 3 equals 0. Well, x equals 3. Maybe. If not, well, maybe x equals -2, because that's a solution to this equation. Or x equals -5. Okay. Now, the nice thing about this is that every one of these factors is either going to be linear like this, which is really easy to solve. Equations are really easy to solve, or it could be quadratic, which is also really easy to solve if you remember the quadratic formula. Okay. So now we have a partial picture of this function. Its zeros are at -5, -2, and 3. So let's see, -5 is the biggest number. So here I'm going to just draw the line x equals -5. Of course, you'd label -5 on the axis. X equals -2, which would be a little closer to the y-axis than to the x equals 5, -5. And x equals 3, which is going to be maybe about here. So now we know the graph goes through all three of these points. Okay. What else? Well, we can find the y-intercept. Y-intercept is when x equals 0. So we just replace all our x's by 0 because x is 0. And we get -3 times 4 times 5. And we find that y is -60. So that on our scale here, well, we now have a scale for our y values. Now, these are the only places the graph can go through the x-axis. Only here, here, here. This is the only place it can go through the y-axis. For reasons we don't have time for right now, but which you can understand from the open math assignments. This thing starts way down here. Comes up through this point here, down through this point here, maybe down a little further, and back up through this point here. And here's an approximate graph of y equals p of x, showing that the thing gets really big when you move to the right, really big but negative when you move to the left, and goes through the x-axis at these 3 points and the y-axis at this point. It has a peak here and a peak here at points that you can estimate. And that's what a polynomial looks like. Now, there's more to it than that, but this is a good start, and let's see what you can do with the homework. You might need to review this video sometimes. Okay.